All right, now we are going to look at some individual gas laws that all come from our ideal gas law, but I wanted to show you a couple of examples here. I have a balloon that is at room temperature. The pressure is staying constant. We're not doing anything with the pressure, and we're not changing how much air is in the balloon, so N, or the moles, is staying constant. But we are going to change the temperature. So temperature, yes, it's at room temperature, but we're going to pour liquid nitrogen on it, which is very, very, very cold. So observe what happens.
200 degrees Celsius, and we're going to slow down these gas molecules enough to hopefully deflate this. Let's do it.
So we're not really deflating it. There's no hole in the balloon.
I've got an obnoxious light there for a reason. I'll show you. I'm trying to really deflate this balloon. And you can see clearly that the balloon requires less space for the gas because the gas is moving slower. So the volume is decreasing. Okay, I'm really going to try to deflate this. The volume is decreasing as the temperature drops. This is a proportionate relationship. As temperature drops, so does the volume of the gas. Okay, temperature, volume. That's the Charles law. Okay, now.
So you see how tiny that balloon got, because as temperature decreased, the volume decreased. And as he said, that's a direct proportional equation here.
Pick this up, and if you can see with this light, I'm going to try to show you, there's some solids on the bottom. And the reason why I'm showing you the light is on the bottom, you can see some solids.
Watch,
you can shake them and hear them, and that's dry ice.
Temperature increases.
Okay.
The volume
so we actually have some
increases.
dry ice solids you can see. But as this warms up, okay, this balloon will in fact take on its old shape as it warms itself up.
So as temperature increases, the volume increases, and those are directly proportional, and this happens to be what's called Charles's law. So going back to look at my ideal gas law, looking at PV equals nRT. In this case, I specifically wanted to look at how volume and temperature were related. So if I look at this equation, I can see that volume and temperature are on opposite sides of the equation. And so, as we just saw, that when temperature decreased, volume decreased, and I'm going to put that over here. When temperature decreased, volume decreased, and when temperature increased, volume increased. And because of this, they have a direct relationship. Also notice that they are on opposite sides of the equal sign. So we can say that volume is directly proportional to temperature. Now, if I had to take a guess, how do you think that pressure is related to temperature? Well, again, they're on opposite sides of the equal sign. So let's just take a gander and let's see, is pressure directly related to temperature? All right, for this next experiment, we're looking at pressure and temperature. So we're looking at this pop can. We're going to put a little bit of water in this pop can, and there is regular room temperature water in this bowl, and the guy is going to put this pop can on the stove to heat up the water that is in the can.
Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Let's look at this experiment a little closer. Before we heat our can, it's filled with liquid water and gaseous air molecules. Heating our can adds energy to our liquid water. The more energy we give our water molecules, the more excited they get, and the further apart the molecules spread. Once enough energy has been added to our liquid water, it changes state from a liquid to a gas. This gas is called water vapor. As our water vapor fills our can, it presses against the sides of our can, creating an increase in pressure.
So increase in temperature, increase in pressure.
When we place our hot can upside down in our cold water, all the water vapor molecules that fill our can get really close together and turn into a few drops of liquid water. This liquid takes up a lot less space than a gas. Water in its liquid state doesn't exert nearly as much pressure on the inside of the can as it did in its gaseous state. At this point in our experiment, the outside atmospheric pressure is much higher than the pressure inside the can. In nature, pressures want to be balanced or in equilibrium. This imbalance causes the can to violently collapse, creating a balance between the pressure inside and outside of the can. This violent collapse toward the center of the can is called an implosion.
Well, that's it.
All right. So we were just able to see the relationship and example of Gay-Lussac's law, where pressure and temperature are, again, directly related. We can see that when pressure increases, or when temperature increases, pressure increases. When temperature decreases, pressure decreases. Again, they're on opposite sides of the equal sign. So we've looked at temperature and volume, which is Charles's law, pressure and temperature, which is Gay-Lussac's law. And I want you to take a second and looking at PV equals nRT, I want you to think about how P is proportional to N, which is moles, and how V is proportional to N. Hopefully you saw the trend that because they are on opposite sides of the equal sign, we can say that pressure is, again, directly proportional to moles. So as one increases, the other increases. As one decreases, the other decreases. And same with volume is directly proportional to moles. As moles increase, volume increases. As moles decreases, volume decreases. And that is our Avogadro's principle. N being directly proportional to pressure and volume. Now let's look at an example of Boyle's law. All right, so this next example, we have these peeps that are very airy, hooked inside this vacuum chamber where when we turn this on, it's going to suck all of the air out of that container. So the pressure is going to go way down inside. So we're going to see what happens to these peeps. There we go. As the pressure goes down, we can see the volume of these peeps going up, 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 up. And this is called an inverse relationship. And you can see how they very quickly deflate when pressure goes back up, then the volume goes down. Here's another example of a balloon put into a vacuum chamber where we can see how when pressure decreases, the volume of the balloon increases. Hear that vacuum.
Look how big it's getting. It's going to fill up our whole chamber. Might pop. Whoa. Whoa. Square balloon. That's so cool. I just made a square balloon, everybody.
Look at that from different side. Squish back down.
Now they've increased the pressure, decreasing the volume.
Wow, that was cool. It
Of
filled
that
up the whole
balloon.
chamber.
So Boyle's law just showed us how volume and pressure, PV equals nRT. So we can see that volume and pressure are on the same side of the equal sign, and so they are inversely proportional variables. So we would write that my pressure is inversely proportional to volume. So as one increases, the other must decrease. And if you think about it, if I were to write this in simpler terms, let's say that nRT, we multiply all three of those together, and we got, let's say a simple number to work with would be 6. All right, so let's say I have P times V equals 6. Let's just say I had a pressure of 1 and a volume of 6. 1 times 6 equals 6. Well, let's say I increase my pressure from 1 to 2. Okay, so I'm increasing my pressure. That means my volume needs to, in order for this right side to still equal 6, 2 times what is 6? Well, 3, right? So if I increase my pressure, so from 1 to 2, my 6 volume had to decrease to go to 3 to still have the right side equal that same amount. So as one increases, the other must decrease. Now we're going to move on and we're going to look at some of these specific formulas. So all of these different ones, pressure and volume, like we said, Boyle's law. So we have Boyle's law, which is P1V1 equals P2V2. So what this is saying is that when I have a gas and I know its initial pressure and its initial volume, I can use this inverse relationship to see what happens if I increase that pressure. What will its new volume be? And similar to Charles's law, I know that volume and temp are directly proportional. So if I know my initial temperature and my initial volume, I can then, if I know what temperature I increase it to, I can figure out that volume. And same with Gay-Lussac's law. And then we're going to look at this combined gas law, but just very briefly. What's really important to remember with these equations is that anytime I'm dealing with temperature, temperature must be in Kelvin, not in Celsius. So when we get into Celsius, we can have negative Celsius temperatures, and having a number that's over a negative number, it just doesn't work for the calculations. The second thing to remember for these calculations is that units must match. So we're not using the ideal gas law, PV equals nRT. We don't have that R constant where it says that I have to have units in liters and atmospheres. So you can have milliliters. You can have, but if you're using volume with milliliters, then your other volume must be in milliliters. We can't compare liters to milliliters. And same with pressure. If we're using atmospheres, then that's great. Just make sure that both of your pressures are in atmospheres. If you're using millimeters of mercury, that's great. Just make sure that both of your pressures, let's say you're using Gay-Lussac's law, your P1 and your P2 both need to have the same unit, whether that's torr, whether that's PSI, it doesn't matter. We don't have to be, like I said, the same units as the ideal gas law, the R that we used. Just make sure that your units are consistent. All right, so if we look at this sample problem from your homework, We are told that 189 milliliter sample of argon gas changes pressure from 775 millimeters of mercury to 405 millimeters of mercury. So I'm changing pressure from pressure 1, which is what it tells me here, to, when it says that, that implies that that's my second pressure. If the temperature remains constant, so T is constant, I don't need to worry about any changing for temperature. What is the final volume? Okay, so that means final volume, V2 is question mark. Okay, well, I am given my initial volume. So then I need to go, okay, that equation that connects volume and pressure, so P1 V1 equals P2 V2. So it wants to know the final volume. V2 is I got to figure out what V2 is. So I'm going to get V2 by itself and divide both sides by this P2. So we know that to get my second volume is P1 V1 divided by P2. So now we're just going to plug in what I'm given. My first pressure is 775 millimeters of mercury times V1, which is 189 milliliters, all divided by P2, which is 405. And if you plug that into your calculator, you should get 362 milliliters. And if we look, those two units cancel out and I'm left with milliliters. And the last thing that this question wants is my final volume in liters. Remember that 1 liter is equal to 1,000 milliliters. So I would just need to convert my answer, remember 1,000 milliliters for 1 liter. And again, I had to put my milliliters on the bottom because I need those to cancel out and I need liters. So it would be 362 liters. All right, so one more practice problem. We see here that we have a 10-liter sample of oxygen gas at 45 degrees Celsius and 0.350 ATMs. Okay, so we've got a lot of info here. This is a volume, our first volume, our first temp, and pressure. Those are all together. It's heated to a pressure of, here's our new pressure. If the volume remains constant, so my volume is not changing. So my volume 1 and volume 2 are going to be the same, so I actually don't even care that I have a 10-liter sample of it. What is the final Celsius temperature? So T2 question mark. So here, notice I have an initial temperature, initial pressure, a second pressure. I need to find the second temperature. So I'm going to flip back to this and look at, okay, temperature and pressure, temperature and pressure. Here we go. We're going to use this where I have P1 over T1. So P1 over T1 equals P2 over T2. Now, I need to solve for T2. So trying to solve with fractions can be kind of tricky. So let's make it so it's not a fraction and so that we have a linear problem. So to get rid of T2, I would multiply, since it's in the denominator, I'm going to put it up in the numerator. So whatever I do to one side, I have to do to the other side. So I'm going to have T2 over here. So that crosses that off. So if I were to rewrite this, then I would just have P2 on the right, and on the left I'm going to have T2 P1 over T1. Well, that's great and everything, except I don't want to solve for pressure 2. I want to solve for T2, but notice I still have a fraction. I haven't solved getting rid of fractions quite yet. So let's get rid of this fraction on the left-hand side. So to get rid of T1 on the bottom, I have to multiply it on both sides, right? T1. Okay, so that gets rid of T1 on the left. So now that leaves me with T2 P1 equals P2 T1. Okay, good, we're making progress. Now I can say, how do I solve for T2? If I look at this, let's see, I'll use orange here. To solve for T2, I want that by itself, so I'm going to get rid of P1. So divide both sides by P1. So T2 is equal to P2 times T1 over P1. Perfect. Now I'm going to get rid of some of this mess, so copy that down if you need to. Okay, so now we've got our equation for how to solve for T2. And remember I told you that my temperature needs to be in Kelvin. So I've got 45 degrees Celsius. So I need to do 45 plus 273.15. So that's going to give me a temperature of 318.15 Kelvin. And that's my T1. Okay, so here we go. So let's plug it in. T2 is equal to P2, which is 0.800 ATMs, times T1, 318.15 Kelvin, all divided by P1, which is 0.350 ATMs. All right, now let's make sure everything cancels out. Atmosphere is atmosphere, so I'm going to be left with Kelvin. So 0.8 times 318.15 divided by 350. So my second temperature should be 727 Kelvin, which is great. But I got to look at this question one last time, and it says, what's its Celsius temperature? So let's just convert from Kelvin back to Celsius. So I just need to minus 273.15. And I have 3 sig figs here, 3 sig figs there. So I need 3 sig figs for my final answer. I should get 454 degrees Celsius. Awesome. Okay, hopefully you got the same. I am going to show you one more experiment video with combined gas law, and hopefully you can feel pretty comfortable with manipulating these variables and working through these different gas laws problems. All right, so the next experiment we're going to look at is looking at temperature versus pressure.
Drop it into your beaker and place your egg over the top.
Yay!
Let's try that again, this time with a glass bottle. To remove your egg from your bottle, use heat-resistant gloves or tongs and hold your bottle upside down over some boiling water, with the egg covering the opening. As the air inside the bottle heats up, it's going to force the egg into the opening. Once it gets stuck into the opening, flip it right side up and continue to heat the bottle until the egg pops out the top. Let's look at this experiment a little closer. This experiment is a great example of the combined gas law, which combines the 3 laws of gases, Charles's law, Boyle's law, and Gay-Lussac's law, and states that the temperature, pressure, and volume of a gas are related. To learn more about the 3 laws of gases, check out our other videos. Normally, when you place an egg on top of the bottle, it won't fit through the bottle's opening, because the egg's diameter is larger than the opening of the bottle. Since the pressure inside and outside of the bottle are the same, The only force that pushes the egg into the bottle is gravity, but gravity isn't strong enough. Our bottle is full of air molecules. When we drop the flaming piece of paper into the bottle and seal the opening with the egg, the flaming paper heats up the air molecules inside the bottle. When a gas like air is heated, the molecules move faster and try to spread further apart, but because the air is trapped inside the bottle, the volume of space that it can take up is limited. Once the air has filled the volume of the bottle and cannot spread any further apart, the air molecules start to press against the walls of the bottle, and since the walls won't move, the air pressure inside the bottle increases rapidly. As the pressure and temperature of the air inside the bottle increases, some of the oxygen molecules are used in combustion, creating the products carbon monoxide, carbon dioxide, and water vapor. Once the pressure inside the bottle is strong enough, it will cause the egg to jump up and down and allow the air to rush out into the environment. Both of these processes reduce the amount of air inside the bottle, but because the air is extremely hot, its volume still fills the bottle and the high pressure remains. Once the majority of the air molecules have escaped the bottle or are used in combustion, the flame of the paper will extinguish. Once this happens, the air inside the bottle will begin to cool, reducing in volume and pressure. But because we have far less air molecules inside the bottle than when we started, the pressure inside the bottle drops much lower than at the start of the experiment. Because the pressure outside our bottle is higher than inside our bottle, the force the outside pressure exerts on our egg is strong enough to gently push the egg through the small opening and into the bottle. Once the egg is in the bottle, the seal preventing air from entering the bottle is gone, and air rushes in, balancing the pressure inside and outside of the bottle. The opposite effect occurs when we remove the egg from the bottle. As we heat the
So this is a great example of showing how pressure, volume, and temperature are all related with which we said is our combined gas law.